its outer and inner measures are equal. Okay, the outer measure equals to the inner measure. The measure M of E is of a measurable set E is the common value of its outer and inner measures. Okay, as we mentioned before. Theorem 2.16, there is a bounded open set is measurable and its measure is the same as defined in section 2.1, the measure of an open set, and a bounded closed set is measurable and its measure is the same as defined in section 2.2. The claims follow immediately from some theorem in the previous section. Let E be a subset of an open bounded interval I. Then E is measurable if and only if the set I minus E is measurable. Okay, because if I minus E is measurable, I minus E is measurable, and I is measurable too, so is E. And we have furthermore M of E, the measure of E plus the measure of I minus E is the measure of I, or the length of the interval I, provided that one of the sets E and I minus E is measurable. If E is measurable, then so is I minus. And if I minus E is measurable, then so is E. For the proof, by theorem 2.15, we have the outer measure of E plus the inner measure of I minus E equals to the measure of I, the length of the interval, by replacing the set E with the set I minus E in the above equality. We obtain the inner measure of E plus the outer measure of I minus E equals to the measure of I, and therefore the outer measure of E minus the inner measure of E will be the outer measure of I minus E. This one and this one will be omitted. The measure of I minus E minus the inner measure of I minus E. And so if E is measurable, then both of the in the left of the equality are the same, and it will be 0, and so is the right side. Okay, and if I minus E is measurable, then the outer measure is equal to the inner measure. So the right hand of the equality will be 0, and so is the left hand of the equality. The property of the Lebesgue measure M, known as its countable additivity or sigma additivity, is the result of the next theorem. The next theorem says that the Lebesgue measure M, we call the measure Lebesgue M, and in some text we see this by lambda. Okay, and here we call the Lebesgue measure M. It says that the measure of sigma additivity. I wanted to explain you sigma additivity property. The measure of the union of EI where I belongs to J if the sum of the measures of EI belongs to I, provided EI intersect with EJ is the empty. Okay, the eyes are disjoint. Now we have here in 2.18, let a bounded set E be the union of a finite or countable family of pairwise disjoint measurable sets. So E is the union of EI, where I belongs to J. Then the set E is measurable, and the measure of E is equal to the sum of the measures of EI where I belongs to J. By the theorem 2.14, the family of the inner measures of EI is summable. Okay, theorem 2.14 states that if a bounded set E is the union of finite or countable family of pairwise disjoint sets EI, then the inner measure of E is greater than or equal to the sum of inner measures of EI, where I belong to J. Okay. Now the family of the inner measures of EI, where I belong to J, is summable, and we have this inequality. The inner measure of E is greater than or equal to the sum of inner measures of E i's where I belongs to J, and it is equal to the measure of the sum of the measures of EI, because each EI is measurable. Each EI is measurable, so the inner measure of EI by definition is equal to the measure of EI. But by the above definition, we have seen before. And by theorem 2.13, the outer measure of E is less than or equal to the sum of the outer measure of EI's where I belongs to J. And so, because EI is measurable, we have and the outer measure of EI is equal to the measure of EI. So we have this one. The outer measure of the inner measure of E is greater than or equal to the sum of the measures of EI, and the outer measure of E is less than this one. But we have the outer measure is less than or equal to the inner measure. Okay, the outer measure of E is less than or equal to the inner measure. So I think we are done. Okay, the inner measure is less than. Sorry, the inner measure is less than the outer measure. So we have the sum of measures of EI is less than the inner measure of E is less than the outer measure of E, and it is less than or equal to the sum of the measures of EI. Then both sides are equal, so is the middle inequality would be the equality. So M star down star of E equals to the outer measure of E, and so E is measurable. The next two theorem asserts that the set of measurable sets of real numbers is closed under finite unions and intersections. Okay. If EI is measurable for each I belongs to J, and J is finite. J is finite, then this union is a measurable set, and of course its intersection EI, I belongs to J. Now theorem 2.19 says the union of a finite family of measurable sets is measurable. The union of a finite family. Let E be the union of EI, where I belongs to J. J is a finite set of cardinality n, and the sets EI and are measurable. For each I belongs to J are measurable. For a given I in J, and an arbitrary positive epsilon is a bounded open set GI containing EI. Yes? Any problem? Oh. By the definition of the infimum, there exists a bounded open set GI, superset of EI, and a closed set Fi subset of EI such that M of EI equals to M star of EI is larger than M of GI minus epsilon over 2n, and dually M of EI equals to the inner measure of EI is less than the measure of Fi plus epsilon over 2n. That is M of, from these two we have M of GI minus M of Fi. These will be omitted. Okay, M of GI minus M of Fi is less than epsilon over n for all I belongs to J. The set Fi and GI minus Fi are disjoint, and the union is the set GI. Okay, these sets are measurable because Fi is closed and GI minus Fi equals to GI intersection with the complement of Fi is open. Hence, by theorem 2.18, we have the measure of GI minus Fi is equal to the measure of GI minus the measure of Fi. Now, let F be the union of Fi where I belongs to J, and G be the union of GI where I belongs to J. Clearly, F is a closed set. G is an open set. F is closed because J is finite, and G is open. Every GI is open, so is the union of them, and both sets are bounded. Arguing as in the previous paragraph, we obtain M of G minus F equals to M of G minus M of F because G minus F equals to the union of GI minus F, and it is the union of GI minus F, and it is the subset of this union of GI minus Fi. GI minus Fi. Because Fi, each Fi is a subset of F. F is the union of Fi. Okay? F is superset of Fi for each I. So this set GI minus F is a subset of GI minus Fi, of course. So their union is. Where all sets on the right and left sides are open, these are open. We have by theorem 2.2 and 2.4 that the measure of G minus F is less than or equal to the sum of the measures of GI minus Fi, where I belongs to J, because F is a subset of E, subset of G. We have this one, M of F is less than or equal to the inner measure of E, it is less than or equal to the outer measure of E, and it is less than or equal to the measure of G. Therefore, by 2.5 and 2.7, we have the outer measure of E minus the inner measure of E is less than or equal to the measure of M minus the measure of F, and it is equal to the measure of G minus F. And we saw that it is less than or equal to the measure of the sum of the measures of M, the measures of Gi minus Fi, and it is, of course, equals to the M of Gi minus M of Fi, where I belongs to J, and it is less than epsilon because of this. Because of this, Mi minus M of Gi minus M of Fi is less than epsilon over N. So their sums M of Gi minus M of Fi, where I belongs to J, is less than epsilon over N. I belongs to J, and because the cardinality of J is equal to N, it will be epsilon. Okay. The desired result follows because epsilon is arbitrary small number. And theorem 2.20 is the same, is parallel to the theorem 2.19. The intersection of a finite family of measurable sets is measurable. And I will leave it to you. Okay, more algebraic properties we have. Until now the union of measurable sets I equals to 1 to n, and the intersection of measurable sets I from 1 to n are both measurable. Now, more algebraic properties with respect to the set theoretic operations of the set of measurable sets of real numbers are established in the following theorem. Let E1 and E2 be two measurable sets. Okay, we have E1 union with E2 is measurable. E1 intersection with E2 is measurable. And now we want to say that E1 minus E2, E1 except minus E2 except E2 is measurable. E1 symmetric difference E2 is measurable. In addition, if E1 is a subset of E2, then E1 minus E2 is measurable. E equals to E1 minus E2, yes, is measurable, and the measure of E equals to the measure of E1 minus the measure of E2. It's very important. For part I, let I be an open interval containing the union E1 union E2, we have E1 minus E2 is equal to E1 minus E1 intersection with I minus E2. It's E2 complement, okay? E2 complement, or E2C with respect to I, okay? You remember that we can write A minus B to A intersect B prime or B complement, okay? Now we have this here, E set minus E2 equals to E1 intersection with I minus E2 by theorem 2.17 and 2.20. The set E1 minus E2 is measurable. For the second part, E1 symmetric difference to E2 is the union of these two, and by part 1 we are done. And for 3, by theorem 2.18, we have the measure of E1 equals to, note that E1 is a subset of E2. Okay, and here is E1 minus E2. E1, E2 minus E1. Let me see if E2 is a subset of E1. Okay, E2, it's E1. E2 minus E1 equals to E. So we wanna prove that the measure of the shaded part of this shape is of this figure is the measure of E2 plus the measure of E. The measure of E2 plus the measure of E equals to the measure of E1, because sets E2 and E are disjoint, and their union is the set E1, and they are done. The set of measurable sets of real numbers is also closed under countable unions and intersection. We proved this for finite union and finite intersection. And now we want to prove this assertion for the case of countable union and countable intersection. Before we need a lemma, before the proof we need a lemma 2.7 says that it En be a sequence of sets, and E equals to the union of EI from 1 to infinity, then the sets A equals to E1, A2 equals to A2 minus E2 minus A1, okay, E2 minus A1, A3 on and on to AN equals to EN minus the union of AI from I to N minus 1. These are pairwise, disjoint, and the union is E. Of course, the union is E. So the union of AI from 1 to infinity will be E, and we have AI intersection with AJ equals to the empty set where I is not equal to J. Okay, it's very easy to prove. It's elementary. The main theorem. Let a bounded set E be the union of a countable family of measurable sets EI. Countable family of measurable sets EI is equal to the union of EI where I belongs to J. Then the set E is measurable. Set E is measurable. For the case of disjoint, we have seen that E is measurable before. Now we have EI such that they are not necessarily disjoint. We may assume that J equals to N because J is countable. Okay, let A and B the sequence of sets from the previous lemma. A straightforward inductive argument using theorem 2.19 and 2.21 shows that the sets N's are measurable. By lemma 2.7 and theorem 2.18, the set E is measurable too. The intersection of a countable family of measurable sets is measurable. This one, theorem 2.22, is for the case of union, and now we have the case of intersection. The intersection of a countable family of measurable sets is also measurable. You can see the proof, nothing to explain. Now we have the notion of continuity, the concept of continuity, by means of the sequence, by means of increasing and decreasing sequence of sets. Let En be a sequence of measurable sets such that E1 is subset of E2, subset of En, and so on. And the set E be the union of these sets is bounded. The union set is bounded. We suppose that E is bounded. Then M of E equals to the limit of M of En. This is the continuity of M. Continuity of M. Says that M of limit of En by this one, it means that E1 is subset of E2 and so on. When n belongs to infinity is the limit of M of M of En when n or as n tends to infinity. Continuity of the measure. Because measure is a function, okay? Measure is a set function. It's a function from, for example, P of R, or subset of R, to this interval from 0 to infinity, and of course to closed infinity. Contains the infinity. Okay, we have this one. We are supposed to prove this. By theorem 2.22, the set E is measurable. Of course, the set E is measurable by the previous theorem, not the previous. The theorem 2.22 says that the union, any countable union of measurable sets is measurable. So is E. E is measurable. It is clear that E is the union of this disjoint sets E1, E2 minus E1, on and on to EI plus 1 minus EI, on and on to infinity. These sets are disjoint, pairwise disjoint. Hence, by theorem 2.18 and 2.21, we have M of E equals to M of E1 plus M of E1 plus the sum of M of EI plus 1 minus M of EI. I comes from 1 to infinity. The partial sum of the series on the right side, this one, is M of E1 plus M of EI plus 1 minus M of EI I from 1 to n minus 1. And it is M of En. M of En. Therefore, M of E is equal to the limit of m of En, where n as n tends to infinity. We have the reverse for the sequence of for decreasing sequence of sets. We have the limit of measures, the limit of the measure of limit downward of En, n tends to infinity, equals to the limit of m of En, where n approaches to infinity. The proof is similar to that of 2.24 and left to the reader, of course. Translation invariance of measure. What is the translation? For any given real number a in R, the transformation PA from R to R given by PA of x equals to x plus a. It's a transformation by a. Okay, transformation by a. It's said to be a translation. So a translation is a transformation by a constant a. The image of a set E under translation PA will be denoted by E plus A. So E plus A is the set of x plus A where x belongs to E. The following theorem lists properties of translations that can be readily verified. And you are supposed to prove this in exercise 2.31. Theorem 2.26, let VA be a translation of R, then VA is a continuous bijection from R onto R. It's obvious. The image of an open set under VA is an open set. Let G be an open set. The component intervals of G plus A are exactly the images of the component intervals of the set G under translation PA. For part 2, a question arises as, is this true for closed case? Think about this. The goal of this section is to establish the following result. The measure of a translation of a set is equal to the measure of the original set. Okay? M of E plus A equals to M of E. In words, the measurability property of sets is invariant under translations, and the measure of a measurable set is translation invariant. We give the proof of theorem 2.27 as a sequence of lemmas. First, for an open interval, we prove m of I plus a equals to m of I. It is obvious. And then for an open set, a bounded open set G, we prove that m of G plus A equals to m of G. Because G is bounded, so is G plus E. It is measurable by theorem 2.26 part 2. Let I belongs to J be the family of component intervals of G by the previous lemma M of I plus A equals to M of I. And hence by theorem 2.26 we have M of G plus A equals to the sum of M of I plus A, and by the previous lemma these are the same, and so we have M of G plus A equals to M of G. This is for closed. And finally for bounded sets, let E be a bounded set and Phi A be a translation of R, then the outer measure of E plus A equals to the outer measure of E, and so we have dually the inner measure of E plus A equals to the inner measure of E. We proved section 1, part 1, and the proof of 2 is similar to that of 1. For a given epsilon greater than 0, let G be an open set containing E. We want to prove this such that M of G is less than M, the outer measure of E plus epsilon, because the outer measure is an infinite. The outer measure is an infinite. So, in as much as E plus A is a subset of G plus A, we have, by previous lemma, the outer measure of E plus A is less than or equal to the outer measure of G plus A. And it is equal to the measure of G plus A. The measure of G plus A. And by the previous lemma, it is equal to the measure of G. It is less than the outer measure of E plus epsilon by this. So, because epsilon is arbitrary, we have the outer measure of E plus A is less than or equal to the outer measure of E. By this inequality, replacing E by E plus A and A by minus A, we have this. The outer measure of E is less than or equal to the outer measure of E plus A. So we have the outer measure of E plus A is equal to the outer measure of E. And for part 2, we will do similar.
دکتر برای امروز بسته
همین تمامه دیگه. تا همینجا همین 2 خط مونده.
2 ساعت و نیم
تمامه دیگه، یعنی 2 دقیقه دیگه تمامه. 2 دقیقه.
ممنون، دستتون در نکنه.
خواهش می‌کنم. Set by the previous lemma, we have the outer measure of the translation of E equals to the outer measure of E equals to the inner measure of E, because E is measurable, okay, and it is equal to the inner measure of the translation of E for any translation Phi A. It follows that Phi A E is a measurable set which has the same measure as E. And finally, we have this. The measure of the translation of E is equal to the measure of E. Okay? You are tired, I know. We will have a lecture tomorrow, and we will set in WhatsApp group, okay?
دکتر فردا روش تحقیق داریم ساعت 5.